Welcome to the Explainer. Historically, trying to integrate artificial intelligence into mobile apps meant bracing yourself for massive cloud bills, high latency, and just huge privacy headaches. But what if you could bypass the cloud entirely? If you're a developer focused on bringing cutting-edge machine learning directly to your users' devices, well, you're in exactly the right place. Today, our goal is to completely demystify the process of adding powerful, on-device AI to Android applications using a highly structured toolkit approach. We're going to scale the complexity ladder together, starting from basic computer vision tasks, moving through natural language processing, and going all the way up to advanced generative AI using an on-device Retrieval Augmented Generation, or RAG pipeline.
Okay, let's dive into this. Here is our roadmap. First, the Google AI Edge Toolkit. Second, classifying images on Android. Third, detecting text languages. Fourth, building on-device RAG. And finally, compiling custom archives. It's a clear, step-by-step journey up the complexity ladder to give you a complete utility belt for modern AI integration.
Section 1. The Google AI Edge Toolkit, Demystifying On-Device Machine Learning. Let's start by establishing the absolute core foundation of our developer utility belt.
This is where Google AI Edge and MediaPipe solutions really come into play. Think of this suite as your ultimate bridge between incredibly complex AI models and your actual application code. The beauty of this toolkit is that MediaPipe handles all the heavy lifting right under the hood. You don't have to spend your precious development time wrestling with complex AI math, C++ JNI nightmares, or intricate tensor memory management. Instead, you get to focus entirely on what actually matters, building amazing, responsive features for your users using these fundamental, pre-built components.
Section 2. Classifying images on Android, focusing on vision tasks. Let's step onto the very first rung of our complexity ladder by looking at standard image classification.
Now, what's really interesting about this setup is how it establishes a highly repeatable, four-step developer workflow. This isn't just for image classification. You're going to see this exact same architectural pattern crop up across tons of different APIs. First, you declare your specific dependency, so in this case, tasks vision inside your Gradle build file. Second, you download your trained model asset, which gets bundled locally. Third, you create the task feeding it configuration options like your desired running mode. And finally, you just run the task to fetch your results. It is clean, it's predictable, and it makes your code incredibly modular.
And MediaPipe makes this workflow incredibly versatile because it natively supports 3 distinct input types. You can process static, still images, pre-recorded video files, or, and this is the most common for modern mobile apps, live video streams straight from the device's camera. But remember, as an Android developer, when you're running that live stream mode, you absolutely must set up an asynchronous result listener. The AI task doesn't block the thread, it returns immediately and just invokes the listener when it finishes processing a frame. If you try to run synchronous processing on a live 60 frames per second feed, you're going to block the user interface thread. And we all know that leads to drop frames, terrible user experiences, and yeah, the dreaded ANR, application not responding crash dialog. No thanks. Once your task is running smoothly without blocking the main thread, you need to manage what it actually outputs, right? You have 4 key configuration options at your disposal: max results, score threshold, category allow list, and category deny list. So the crucial point is that you have complete control to cleanly filter out unwanted noise or set strict confidence thresholds directly within your app code. And you can do this without ever needing to modify or retrain the underlying machine learning model. Say you're building a hot dog identification app. Just set your category allow list to hot dog and let the framework seamlessly block out all the other noise without you writing a single line of custom filtering logic. It's a real game changer. Moving right along to Section 3, Detecting Text Languages, or NLP at the Edge. Let's step up to the next category in our toolkit, shifting away from pixel data and into natural language processing. Notice a familiar pattern here? This just reinforces the absolute beauty of progressive disclosure in this API design. The workflow is almost perfectly identical to the vision task we just talked about. All you're doing is swapping your Gradle dependency to tasks text, providing your downloaded language model, creating the task, and calling the detect method. Instead of you writing complex parsers to break sentences down into recognizable tokens, the framework handles all that messy data pre-processing automatically, right inside that single detect function. To see this in action, let's explore a mini narrative. Imagine feeding the model this exact French quote from our source documentation. Il y a beaucoup de bouches qui parlent et fort peu de têtes qui pensent. Translated roughly, that's, there are many mouths that speak and very few heads that think. Let's actually trace how the on-device model processes this raw string. And this brilliantly illustrates the raw output data you receive in literal milliseconds. The framework took that string, tokenized it internally, and instantly returned a near-perfect probability score of 0.9997 for the language code FR, meaning French. And here is the absolutely crucial takeaway for your application's architecture. No server round trip required, no API latency. You literally don't even need an internet connection. It is fast, completely private, and incredibly accurate.
All right, Section 4, Building On-Device RAG. Delving into advanced generative AI pipelines. Now it's time to ascend to the absolute cutting edge of our complexity ladder. We're setting up a Retrieval Augmented Generation pipeline locally using the LLM Inference API and Gemma 3.1b. Building a RAG pipeline essentially gives your large language model access to custom, user-provided data so it can generate highly accurate, context-aware responses rather than just relying on its base training. Let's walk through this precise 5-step chain. First, you load the user data, say a massive text file stored locally in your app's assets. Second, you apply chunking. Now, this is an art form. Think of it like the Goldilocks principle of data ingestion. If your text chunk is too large, it dilutes the specific context, making it hard for the AI to find exact answers. If it's too small, well, the AI loses the thread of what it's reading and lacks the surrounding context to make sense of the fragment. You really have to find that just right size to slice your documents into. Third, you extract embeddings from those perfectly sized chunks. Fourth, you store those numerical vectors into a standard SQLite database on the device. And finally, you invoke the retrieval and inference chain to orchestrate the whole shebang and generate your localized response. Step 3 of that pipeline, extracting embeddings, presents a massive architectural decision that balances device constraints with user privacy. You have two primary setup options here. You can use the local Gecko embedder, which securely vectorizes text completely on-device, leveraging the phone's own GPU or CPU. This means absolutely zero data leaves the phone. It preserves user privacy perfectly. Alternatively, you can use the Cloud Gemini embedder, which relies on the Generative Language Cloud API and does require Gemini API key. If privacy, zero latency, and offline capability are your ultimate priorities, the local Gecko model is an absolute game changer.
I want to pause on a specific number for a second, 768. When you run that embedder model, it takes your carefully sized chunk of text and turns it into a vectorized numeric representation. 768 is the specific dimension or length of each vectorized chunk that gets securely stored inside your SQLite vector database. Think of these 768 dimensions as the digital DNA of your text chunk, mathematically mapping complex linguistic concepts like tone, subject matter, context, and semantic meaning straight into a coordinate system. The LLM then mathematically compares these 768-dimension vectors to instantly find the closest, most semantically relevant context for whatever the user happens to prompt. It's brilliant.
Let's move to and see how this builds into Section 5, compiling custom archives and shrinking the framework. This is our final optimization phase for all the app architects out there.
Every Android developer out there knows the pain of an oversized app bundle or APK bloat. But here is the brilliant thing about MediaPipe. It doesn't just force a massive generic Android archive onto your project. Because a bloated one-size-fits-all AAR doesn't exist, you as the developer get to compile a highly customized archive. First, you identify only the specific MediaPipe calculators your project actually uses. Next, you define a custom MediaPipe AAR target. And finally, you run a Bazel build command. And yes, I know running a Bazel build command might be an extra step in your Gradle-heavy lives, but it ensures that only the strictly necessary resources and libraries are packaged. This keeps your application incredibly lean, fast, and efficient, all while running state-of-the-art machine learning algorithms.
We have covered a massive amount of ground today. We journeyed from creating highly unified 4-step workflows for standard image classification and text detection, all the way up to orchestrating a complete generative AI RAG pipeline entirely on a mobile phone's local hardware, managing chunking and 768-dimension embeddings without ever pinging a cloud server. You now possess a highly optimized, fully local developer utility belt. The barrier to entry for on-device machine learning has quite literally never been lower, and the offline capabilities have never been higher. So I leave you with this final thought. With text, vision, and RAG pipelines now running locally, securely, and instantly on your users' devices, what will you build next?